Okay, ladies and gentlemen, good afternoon, and welcome to Lesson 4, Fission and Fusion. Now, this is interesting and a little weird, so pay attention. Now, talking about fission. Now, we've talked about radioactive decay before. That is, alpha particle is emitted, or beta negative particle, beta positive particle, or gamma rays emitted. We've talked about that. Now, that happens naturally. Higher energy elements transmute into lower energy. Right? Now, but we can do this, we can cause artificial decay. Okay, it was Rutherford. Seven of spades. Did this in 1919. He took nitrogen, hit it with a high energy alpha particle, and made oxygen. 16. Two, 1. Now, this is neat. He made heavy hydrogen or deuterium. Now, here he broke up a nitrogen. He made something and it split up into an oxygen and a hydrogen. Now that's artificial decay or fission, something breaking up. Now that's not a particularly good example of fission. A better example was Fermi in 1938. He hit uranium-235 with a neutron, and he made 236, which broke down to be 141 barium and 92, 36 krypton, plus 3 neutrons plus energy. Now, I had it crammed in there, my bad, live with it. Now I want to point out a few things about this. Uranium-235 is non-radioactive. That is, it's stable. Okay? Now, guess what we can say about U-236? This is radioactive. That is, it's unstable. And we got new elements. The new elements are barium 141 and krypton 92. And byproducts, energy and neutrons. That is, they're products, but we don't care about them, or we weren't specifically wanting them, so we call them byproducts. Now, this is a classic example of nuclear fission. How do I find that? Breaking apart of a larger nuclei. So uranium-235 hit it with a neutrino, a neutron, sorry, ends up being barium-141 and 92 krypton. Now, so far so good? All right, now, a couple things I got to point out. First thing is energy is released. This is binding energy. So, if we do this slowly and carefully, we have a nuclear reactor where we make heat and we convert that to electricity. We do it rather quickly, we end up with an atomic bomb that goes boom. Now the second thing, this one. Second thing, 3 neutrons. Released. The byproducts. And note, this was started by using a neutron. So, these 3 neutrons could start 3 more reactions, releasing more energy. And 9 more neutrons. Yes, we end up with a chain reaction. And those 9 neutrons could release more energy, hit 9 more uranium atoms, U-235s, and release a lot more energy and 27 neutrons. This is what we call a chain reaction. So, and the chain reaction, if we control it, is a nuclear reactor that makes us energy. So just restarting Mr. Computer. In this particular reaction, it requires 1 neutron. Most of these reactions, it's 2 particles, something hitting something else. The odds of getting 3 particles to hit just at the same time, the right time, the right place, the right energy, the right geometry is freaking impossible. Not impossible, but I'm not going to try calculating the odds. Life is too short. So this is what we call a chain reaction. As I said, if we control it, it's a nuclear reactor. If we don't control it, it's a nuclear bomb. And I put my notes down somewhere. Never mind. So now, here, whatever. So controlled is a nuclear reactor. Uncontrolled is a bomb. Now, I could ask for the. Now note. I could ask for the energy here because this is the binding energy or the mass defect. So, can you guys calculate the amount of energy given off here? Yes. Now, hint, I'd start with 236 uranium. Do that for me, please. U-236 going to barium and krypton and 3 neutrons. Figure out the mass defect and the amount of energy that's missing, please. By that time, hopefully, Mr. Computer's working and we can talk. Ready? Don't turn off your computer. Micro squash. God bless micro squash. Okay. Did I take attendance? No, I didn't. Okay. fraction you're looking at. Finding the mass defect. So, don't expect you to know what these numbers are, but I expect you to be able to look them up. So I'm going to give you the handout on this. Massive selective isotopes. 141 barium. 141 is 140.914 units. Krypton, Krypton 92. 9192. The neutron is, oh, I didn't list it on the sheet. 1.00. What is the neutron? 0.67. Yes. In atomic mass units, it's 1 decimal. Hang on. The front of the sheet, it's 1.00866 units. So it's 3 times this. And uranium 236. Oh shoot! I've only got 235 here. Shoot. Well, then you don't have 236 on your sheet, do you? Yes, I said easiest is to start with 236, but we don't, so you're right. So we have to start with 235. And then in this case, we have a neutron here, and we have neutron, so it'd only be 2 neutrons at the end. Could be 235.043930. That's calculated. Mr. Calculator. Now, if I can completely, actually, let's go over here. Completely hurt his mind. So now the whiteboard's working, I can use that. Go to that beach. Now you realize I exist. You wombat. Beat you with a stick. The magic smoke comes out. There we go. Okay. So, looking at this, you find the difference in masses, and what do you get? Now I don't have a calculator, but 235.043930 minus that gives you a mass deficit of what? A mass defect. Charles, what you get? 0.1? Missing. So turning that into kilograms, plug into E equals mc squared. How much energy are we missing? Well, if you're plugging it into E equals mc squared, you'd have to figure out particles, fission, fusion, so 8665. Then you turn that into kilograms. Now what is it? 1.66056 10 to the 25 times 1u, and that gives you kilograms, and then you go E equals mc squared. What do you get?
I got 3.0. That's minus 28.
Did you square the c? Because this is something to the minus 28 of a kilogram, but then you multiply that by c squared, the minus 6 to the 16 gives you something to the 11. I got one.
I'll just tell you a conversion.
Oh, my bad. I'm sorry. One more time, the mass is
3.0893 times 10 to the minus 8.
kilograms times 3.00 times 10 to the 8 meters per second squared gives you
2.78 times 10 to the minus 11.
it's reasonable.
For the mass deficit, I only did the mass deficit for the uranium 235. Oh wait, never mind. We changed it from 236 to 235. Because I got a different number for the kilograms originally.
Okay. Well, as I said, if you did 236, that's easy if I gave you the mass of uranium 236. I didn't. Turns out it's only 235 on the formula sheet, so you got to go 235 plus a neutron. Now, guys, Charlize did that. That's the answer she got. Is that the answer you guys got? Okay. Thank you. So that's how it's done, and that's the correct answer. Now the board's working, you can do this. Now, okay. So, fusion, two smaller atoms combine to form one larger atom. So in the sun, the net reaction deuterium plus tritium makes helium-4 and a neutron and energy. Now, I've talked about how on going to the moon, one thing we could do on the moon would be to find helium-3 because it's given off, a lot of it's given off the solar flares. But the sun is made up of a lot of hydrogen and some deuterium and tritium, and it makes helium. So all this stuff is being spit out. So if we go into space, well, it's not a perfect vacuum. There's like 8 atoms per cubic meter. And it's made up of this stuff. So hydrogen, helium, deuterium, tritium, all sorts of smaller atoms given off and ions given off by the sun. Now, if you want to copy out this reaction, you can, but I'm going to show you the overall reaction. And it gets kind of complicated. 1, 1, hydrogen, 1, 1, hydrogen. They combine, you get an explosion. Beta positive particle, antineutrino, hydrogen. Another 1,1 hydrogen, you get another explosion. Don't care. 3,2 helium. And another explosion. Okay. Now, I was going to say this gets kind of complicated. As I said, you want to copy this out, great. If you don't, I understand. But you get two hydrogens combining, giving you a beta particle, beta positive particle, an antineutrino, and a 2,1 deuterium particle. That deuterium combines with another hydrogen to give you a 3,2 helium. The 3,2 helium, well, it combines with something else, and you get a couple of gamma rays, a couple of beta particles, and an alpha particle coming off. Now the gamma rays, high energy. So there's a lot to this, and no, you don't have to know this. But that's the overall reaction. 4 hydrogens make, well, I'm going to be quiet and let you look at that. So it's, as I said, no, you don't have to memorize this reaction. And yes, this is kind of complicated, but of what I do want you to notice, you've got 2 of these, and each of these is 0.242 mega electron volts. These 2 reactions, 5.49 mega electron volts. And this reaction gives off 12.85 mega electron volts. Millions of electron volts. So, can you grab Mr. Calculator and tell me the total energy given off here?
You just add them all?
Yeah, add them up. 2 times that, plus 2 times that, plus that. Two times 5.49 mega electron volts.
Do you ever get a question that will give us the diagram and just have to add it, or do we have to figure it out?
No. I've never seen anything like that. They would give you the diagram and ask you questions about it. Or they go, these combine, what's the overall reaction? And they'll give you some of the products. Like they give you this one here and go X, Y, barium. You have to figure out what it is, or something like that. Now, gamma rays. Where's the third? Oh. Sorry, it's 3 gamma rays coming out of this one. And I got 24.67 mega electron volts. Am I correct?
Yep.
All right. Now this is important because this is a heck of a lot more energy than in a chemical reaction. thousands of millions of times more. Much more. So energy released in a nuclear reaction is much more than a chemical reaction, thousands and thousands, often millions of times more. Okay, so far so good? Okay. Would you like a real pencil, Charles? Okay. Now, thing to note here, if we look at binding energy per nucleon, okay. Okay. Now, how does this go? Now, somewhere in your textbook, if you've read it as I've asked, you'll find this graph, binding energy per nucleon versus element, or element versus binding energy per nucleon. And the graph looks something like this. Most stable or highest binding energy per nucleon is iron. Just the way it is. Now, I was going to say, I cannot remember the atomic number for iron, so I'm going to, sorry? 26 sounds right. You're right. Iron 26. Now, is it, I want to say 50, 52, 56. Anyway, one of the iron isotopes is the most stable. So, if you look at this, actually it is on page 825 of your textbook. Don't normally ask you to bring your textbook to class, but tonight look at it. So you'll see here, most stable, hydrogen, helium, blah, 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 blah. So here, smaller than iron, fusion, that is taking two smaller atoms and slamming them together, will release energy. So fusion reaction, we take hydrogen and slam into helium, will release energy. We take helium and slam it together to make lithium or beryllium, we will release energy. We take two carbons and slam them together to make, I can't remember. Anyway, so as long as we end up with something smaller than iron, energy is released. Now, above this, we've got bigger atoms. Fission releases energy. So if we go U-235 or uranium-236 is the best example. We just talked about that. That fission, breaking it apart, releases energy. So you get the most stable iron. So they'll talk, if you do astronomy and rocket science, they talk about iron cores and stars. Once you reach that point, you're kind of screwed. Because there's no more, you've squeezed all the energy out you can. And then you basically die. But here, this is important. Fusion, smaller than iron. Fission, bigger than iron, releases energy. All right? So far, so good? Now, I do want to point out here, we can do fission, that is break apart elements smaller than iron, but this costs energy, or we lose energy. Yes. It's endothermic, that is, we have less energy at the end than we have at the beginning, which kind of sucks if we want to get energy out like a nuclear reactor. At the same time, actually, I should color code that.
So fission, you will need some bladders?
Hang on. No. A net, if we exothermic reaction, if we do fusion with something smaller than iron, we will always get energy released. If we do fission with something larger than iron, we always get energy released. But if we do the opposite, that is fission, I take helium and break it apart to hydrogen, I lose energy because of that bonding energy I have to put in. And the same thing here. If I take fusion, like I take two pieces of uranium and slam them together. I can do that and I can make a new element, but I'm going to lose energy. Like I take barium and krypton. I slam them back together to make uranium. I'm going to lose energy because I have to put in that energy, the binding energy that was lost. So there's quite often a question about this. Where is it exothermic? Where is it endothermic? Iron is the key. All right? Got that?
What do you mean iron?
Well, anything smaller, iron is the most stable. So anything less stable than iron will react. So fusion, that is smaller elements, like if I take two hydrogens and slam them together to make a helium, I'll get energy out. If I take an atom bigger than iron and break it apart, I'll get energy. That's the only way I get energy. Okay? So if I take, literally, I take two atoms bigger than iron and slam them together, I can make uranium, but I have to put in energy. It's endothermic, or I lose energy.
Okay, so on the right side would be an exo?
Yes. Fission, breaking it apart, is exothermic. This releases energy, and fusion releases energy. Now, have you done chemistry recently, endothermic, exothermic? Well, this is exo. This is exothermic. This is endothermic. And this is endothermic. I put in more energy than I get out. Right. Now, usually we want to get energy out like a nuclear reactor for electricity. So.
Yeah, it just looks weird because then can't we say that exothermic loses energy? And yeah.
Well, exothermic loses or gives off energy, doesn't it?
Yeah.
Okay. All right. Now, what was I going to say? I love this, putting my notes down and wandering away. Okay. Oh, right here, right where I left it. Never mind. Now, finally, come on, next page. Now, fission occurs in the sun quite a bit. Now, the problem is we need like 45 million degrees Kelvin and very high pressures to get this to work. Strong force of gravity or force magnetic to get this to work. We've really got to cram them together. So it's basically the center of the sun. It's hot enough and it's high enough pressure. We can get a fission reaction to work on Earth, but we use an atomic bomb to start it. It needs that much energy. We have an atomic bomb. Uranium or plutonium. And that explodes, and that puts enough heat and pressure on some hydrogen to form helium, the hydrogen bomb. And that makes a hydrogen bomb. So, all right, now that's it for me. I want to point out fusion can happen spontaneously with large, heavy elements. We can also force it. I apologize, I erased it, but it was Rutherford hitting nitrogen with an alpha particle, artificial transmutation, we can make unstable elements. And sometimes it takes a lot of energy. Now, the atomic bomb, we can get that spontaneous with a chain reaction. The hydrogen bomb, or fission, God help me. Fusion, I'm sorry guys, I'm having a brain fart here. Fusion, taking two small atoms together and slamming them together. Not fission. God, getting old. Fusion, two small atoms. As I said, on the sun, 45 million degrees Kelvin, very strong gravitational and magnetic fields. We can do it in the Earth, but we have to have an atomic bomb to start it. And needless to say, we haven't made a sustained fusion reaction yet. That would be very nice if it did. Lots and lots of energy. And the only byproduct would be helium, or helium balloons, which wouldn't be bad. Anyway, I'm going to be quiet now because this is embarrassing. Questions? All right, I'll give you your homework.